Hello everyone, my name is Olivier Bernard. I have worked 15 years in the oil refining industry, and for the past 3 years I have been a lecturer at IFP school. I will be your professor for the next subject, crude oil refining. In this section, we will take a look at the crude composition and the different hydrocarbon types we have in crude oil. What is a petroleum cut and how we produce these cuts from the crude oil in the crude distillation unit. Afterwards, in the second part, we will see together the refining processes used to produce diesel and gasoline. From the previous video this week, we have seen with Ludivine the different specifications that have to be met for gasoline and diesel fuel production. During this lecture, we will focus on the oil refining industry, which transforms crude oil into the different final commercial products, including gasoline and diesel. We will see together the different units of a refinery, which control the quality and the specification of the final products. Let's start with the raw material of a refinery, the crude oil. In a barrel of crude, you have approximately 85% of carbon elements, plus 10% of hydrogen. Indeed, a barrel of crude is composed mainly, up to 95%, of hydrocarbons composed of carbon and hydrogen. The other 5% are called impurities. On average, we find approximately 2% of sulfur compounds. The sulfur level in the crude oil is a key parameter for crude selection and crude prices. The higher the sulfur level in the crude, the more difficult it will be to treat the crude to produce diesel and gasoline with a low sulfur specification. In general, the higher the sulfur content of a crude, the lower the price. In all cases, these sulfur compounds must be removed in order to respect the sulfur specification of the final product, for instance, less than 10 ppm in Europe, as already discussed with Ludivine in the previous video. We find other impurities, including nitrogen, typically around 2%, water, salt and sediments, which could be present in the crude oil. Water and salt must be removed from the crude oil at the inlet of the refinery. This is to avoid corrosion problem and fouling by salt deposition in the units of the refinery. Now we will focus on hydrocarbon types that we typically find in crude. In crude oil, you can find naturally 4 types of hydrocarbons. First, we have paraffins. Paraffins are linear hydrocarbons made up of carbon and hydrogen atoms. Long linear paraffins are also called waxes. Secondly, isoparaffins, which are non-linear paraffins with one or multiple small groups of carbon and hydrogen attached to them. The third type of hydrocarbon is the naphtene family. These hydrocarbons are composed of carbon and hydrogen linked together in a ring shape. The last family is aromatic compounds. Aromatics are also hydrocarbons composed of rings of carbon and hydrogen, but with double bonds between the carbon elements. Compared to naphthenes, aromatics have, for the same number of carbons, less hydrogen. The first aromatic is called benzene, with 6 atoms of carbon. In conclusion, a crude oil is characterized by its paraffin, isoparaffin, naphtene and aromatic content. It's important to know the type of hydrocarbon you have in a crude, because these molecules will directly influence the quality of the gasoline or diesel you will obtain from this crude oil. For instance, the research octane number, or RON, of paraffin is very low. These compounds are not ideal for gasoline fuel. On the contrary, isoparaffins and aromatics have a high RON suitable for the gasoline fuel specifications, discussed in the previous lecture with Ludivine. Moving on, consider the cetane number. We find that paraffins have a high cetane number compared to isoparaffin and aromatics. Remember, as seen with Ludivine, if the RON is low, the cetane number is high, and on the contrary, when the RON is high, the cetane number is low. In a crude, we typically have more than 200,000 different compounds. This very high number of compounds means that it's simply impossible to perform precise analysis to all the different compounds of the crude oil. In practice, we divide or we cut the crude oil into different smaller petroleum cuts. We do not need to analyze the real compounds in each cut, but just characterize the cuts using the simple analysis discussed in the previous video, like, for instance, density, sulfur content, boiling temperature and carbon numbers. The crude oil is divided into these different smaller petroleum cuts in the first unit of the refinery called the Crude Oil Distillation Unit, or CDU. At the top of the crude distillation column, we find the lighted cuts, such as gas, and at the bottom of the column, we find the heaviest cuts, such as the residue. Here, I will classify the cut we obtain at the outlet of the crude distillation column. At the top of the column, we have the lighter compounds, with the lowest carbon number and at the lowest boiling temperature. First, we have the gas, with a carbon number between 1 and 4, and with a boiling temperature range lower than 0 degrees Celsius. That means that under atmospheric pressure and at ambient temperature, these compounds are in the form of a gas. We find in this cut gas such as methane, ethane, propane and butane. Then we have the naphtha cut. This cut is the raw material used in the petrochemical industry to produce different types of plastics with different properties. The naphtha cut has a carbon number range between 5 and 6 and a boiling temperature range between 0 and 80 degrees Celsius. The boiling temperature range mentioned here is directly linked to the volatility and distillation curve discussed in the previous video with Ludivine. Next, the gasoline cut is composed of hydrocarbon with 7 to 11 carbon numbers and with a boiling temperature range from 80 to 180 degrees Celsius. This cut is the base of the gasoline fuels used for spark ignition engines. The kerosene cut is the main base to produce jet fuel, called jet, delivered to all international airports. Typically, the carbon number of this cut is between 11 and 13. The next cut is the diesel cut, which is the base of the diesel fuel for diesel engines, cars and trucks. The hydrocarbon chain contains between 13 and 25 carbon numbers. Finally, at the bottom of the crude distillation column, we have the atmospheric residue. This cut is in fact all the heavy hydrocarbons with carbon numbers higher than 25 and with a boiling temperature higher than 360 degrees Celsius. In this table, I have summarized the main uses of the different cuts obtained at the outlet of the crude distillation column. Gas for production of commercial propane and butane, naphtha as the raw material for the petrochemical industry, gasoline and diesel and kerosene as fuels for cars, trucks and planes, and atmospheric residue as heavy fuels, for example, for boats or power plants. Now, let's see in practice the Crude Distillation Unit, or CDU, which is the first unit of a refinery. As we have just seen, the target of this unit is to cut the crude into different cuts. First, the crude is stored in a big oil tank. The crude is heated in heat exchangers. This piece of equipment increases the temperature of the crude by recovering heat from other hot streams up to around 140 degrees Celsius. Then the crude is desalted in a desalter. A desalter is in fact a big horizontal vessel. We can compare this equipment with a washing machine. Fresh water is mixed with the crude to really wash the crude and eliminate all the salt and sediments with the water. Because of the density difference between water and crude oil, we recover the water, including the salt, at the bottom of the desalter, and the crude at the top of the desalter. At the outlet of this desalter, the crude is heated to a higher temperature, first in a second series of heat exchangers, and finally in a furnace. At the outlet of the furnace, the temperature reaches 360 degrees Celsius. At this level of temperature, all the cuts, from gas to diesel, are in a gas form. Only the atmospheric residue remains liquid. This mixture of gas and liquid enters the crude distillation column. By operating the distillation column, we will recover at the top, at around 120 degrees, the gas, then below the other liquid cuts, naphtha, gasoline, kerosene, and diesel. At the bottom of the column, we recover the atmospheric residue at a temperature around 360 degrees Celsius. By playing with the operating parameters of the crude unit, the refiner can regulate the boiling range temperature of each cut and change the initial and final boiling point of the ISTM D86 distillation curve. Finally, by changing the shape of these curves, the refiner can play on different specifications, such as density of the cut, volatility, or cold flow properties. For instance, if the density of a cut is too high compared to the specification, the final boiling point of the cut can be decreased to limit the quantity of heavy products and, in this way, decrease the density. It's important to notice that some specifications cannot be regulated by distillation column operation, such as sulfur content, which needs additional treatment. To finish, I would like to summarize this part. We have seen that at the outlet of the crude distillation unit, we obtain 6 main cuts with different boiling temperatures and carbon number ranges. These cuts are the basis of the commercial products such as gasoline and diesel fuels. But in general, the specifications of the cuts obtained just at the outlet of the distillation column are really far from the targeted specification of the final products. In conclusion, these cuts will need further refinery treatment in specific units to improve the quality of the petroleum cuts and to meet the final product specifications. We will discuss this additional refinery treatment for diesel and gasoline in detail in the second part of this lecture. So that's all for now. See you soon on the next lecture.